Hi and welcome everyone. My name is Levente Csikor and now I'm going to talk about our findings regarding the privacy of DNS over HTTPS. Let's have a quick discussion about privacy and the domain system in general. Since the Edward Snowden case and the mass surveillance of the NSA, privacy became of utmost importance. As one of the main results, today more than 90% of the web traffic is using HTTPS. However, we tend to forget that using HTTPS is not enough. To establish a secure web connection, there are further things happening under the hood, and one of them is that every website visit is preceded with a bunch of DNS queries. The DNS in a nutshell is the phone book of the internet, which translates easy to remember host names to IP addresses. In most of the cases, it is still plain text, which means that even if you are using HTTPS web connection, I might not see the content you consume, but I can see where it comes from. So let's see what are the main three reasons of DNS still being plain text. First of all, historically, there were much less focus on privacy and security. Second of all, DNS is kind of like an overhead, so the simplest it is, the fastest the whole connection can be. Third, and most importantly, there are several services which heavily rely on the plaintext DNS data. So let's see what are these services based on the plaintext DNS data. First of all, your internet service provider is using your DNS data to implement its own firewall, parental control, content caching, or even blocking ads. So there are many useful aspects of relying on DNS data. On the other hand, malicious actors or even authoritarian regimes can use DNS to block website and contents, to spy on the users and monetize the DNS data later for advertising, for instance, or they can also tamper and redirect users to malicious phishing websites. The question immediately arises then, what are the privacy measures we can implement? One of the recent standards is DNS-over-TLS. As its name suggests, it encrypts the DNS communication, thereby hindering malicious actors to spy on or tamper with our DNS traffic. However, it is using TCP port 853, which allows it to easily block it. According to the so-called opportunistic user profiles, once the encrypted DNS is not working, clients transparently fall back to plaintext DNS, so we are back at square one. The recently standardized DNS over HTTPS does not provide any better security measure compared to DNS over TLS, but it is using port 443, which means that it inherently blends into regular encrypted web traffic. Hence, it cannot be filtered, cannot be differentiated, or even cannot be blocked. It also means that all ISP services I mentioned before will break. So at some point there's a constant debate between this enhanced privacy and weakened protection, but this is not the question we are going to discuss here. Instead, in this paper, we investigate whether DOH traffic is indeed indistinguishable from web traffic. To answer the question, we build a supervised machine learning model to identify each DOH and web packet with high accuracy. This means that ISPs can easily filter out DOH packets and force its users to fall back on plaintext DNS. Of course, when it comes to blocking, ISPs need to achieve an extremely low false positive rate to not cause service disruption in the web communication. As our second contribution, we investigate whether there is any countermeasure for our model. To this end, we study a wide set of custom padding techniques, and we found that we can degrade the performance of our model to a certain level where it becomes impractical. The first step in our journey is collecting sufficient amount of data. To this end, we created easy-to-deploy Docker containers with a bunch of scripts to visit the first 20,000 domains in the list of Alexa's top 1 million domain. We used 25 different DOH resolvers, including the most prominent ones. Lastly, we deployed our containers across multiple continents and cities to capture diverse network statistics. Let's see what are the four main properties for our machine learning model and its evaluation. First of all, out of 6 possible candidates, we chose random forest as our basis. For splitting the dataset, we use 90% of it for training and 10% of it for testing. For the features, we rely on simple characteristics that are visible when we eavesdrop on encrypted communications. These are the IP packet length, the previous packet's length, inner packet arrival time or time lag for short, and the previous packet's time length. For the metrics, we use F1 score, precision, and recall with low false positive rates. Last but not least, in terms of settings, we have closed-word setting, where we use the same resolvers and domains visited with respect to the train test split ratio mentioned before. For OpenWord, we devised 2 different settings. One assumes different resolvers, but same domains visited, while the other also assumes different resolvers, but the visited domains are also different. Let's see some results using the data gathered in one location only. In the best case scenario, for training we use the data for the 4 most prominent resolvers, namely Google, Cloudflare, Quad9, and Clean Browsing. Additionally, after our preliminary analysis, we also used 3 further resolvers for which the results were less convincing. The performance of this model is higher F1 score than 0.99 in case of the closed word setting, while 0.975 in case of the open word setting respectively. However, we can see that the FPR values are not that convincing, meaning that on average, around 1 out of 100 web packets will be misclassified, hence dropped. So let's focus on the low FPRs, particularly if only 1 out of 10,000 web packets is misclassified only. In this case, our recall value for the closed and open word setting is 0.974 and 0.9 respectively. From the results, we can also conclude that the performance depends on the resolvers used only and the domains visited are less important. Now let's see the worst case scenario. What we did is we took our model trained in one location and evaluated its performance on the data gathered at other locations and on different architectures. We can see that, again, if we aim at low FPRs, which we do, then the average recall value is around 0.9 for the x86 architecture and around 0.8 for the ARM architecture. Note, this setting, according to our definitions, is a closed word setting. The results indicate that a model is quite robust and can be deployed at any other location. However, since network characteristics can change from even ISPs to ISPs, it is recommended to train your own model. Meanwhile, you can use ours while you're generating yours. Next, we focus on how we can counter our DOH identification model. We haven't got too many options as the identification model uses only a few features. Basically, we can play around with the packet length values and the time lags. Of course, we cannot truncate packets or make our latency better, but we can pad the packets or introduce extra delays. Therefore, the idea is to pad the DNS packets to look more like the web packets. To reach this end, we analyzed 5 different padding techniques. Some are from the literature and some are proposed by us. The first one is using a fixed padding according to an RFC. This pads each DNS query to the closest multiple of 128 bytes. The second option is simply using a random padding. In the third technique, we pad each DOH query to the average web packet. The fourth technique pads each DOH query to a random recent web packet. And finally, the fifth one, which is also the most intricate one, pads a sequence of DOH packets to a recent sequence of web packets. This tries to mimic as the user requested the same content again. First, we concentrate on the packet length features only. So we build a model using only these 2 packet length related features. Note that the training is done on the padded datasets each time. Otherwise, any padding technique would simply disguise a model that was trained on a non-padded data. What we try to grasp here is how effective an ML model can be if the features of the 2 different types of packets are similar. We analyzed each padding technique one by one, and we found that the fifth one performs the best in terms of disguising our model. Hence, we apply this technique on the other features, retrain the model on the new padded dataset, and evaluate its performance. Again, we aim at low FPRs. We can see that in the closed word setting, the recall value of the model drops down to around 50%, which is similar to a simple algorithm using a coin toss to identify a packet as DOH or web. In case of the open word setting, the recall value of the model is practically 0, even if we allow a 10 times higher FPR value, which renders our padding technique very effective against the DOH identification model. Let me conclude our work. First of all, privacy became of utmost importance. However, even if we encrypt our communications on the internet, the DNS can still expose privacy-related information, which can also be used for malicious purposes, like blocking access to certain contents. As a countermeasure, DNS-over-HTTPS has been proposed that does not only encrypt DNS, but is designed to blend DNS traffic into our encrypted web traffic. This results in that it cannot be monitored, filtered, or even blocked to force its users to fall back to plaintext DNS. In our paper, we built a supervised machine learning model to distinguish DOH packets from web packets using only a small set of features. Our model can identify DOH packets with high accuracy in both closed and the open word settings with extremely low false positive rate. In the second part of our paper, we developed the DOH anti-identification model as a countermeasure. We carefully pad the DOH packets to look more like the web packets, thereby disguising the model. In particular, we can drastically degrade the performance of the model to a coin toss game for the closed word setting and to 0 in the open word setting. That's all from our site today. Thank you for attending this virtual session. Our container to gather data, as well as our machine learning algorithm, are publicly available on GitHub and Docker Hub.